Then, thank you for the introduction. And on behalf of Team Hamiltonians, I will present our winning solution for the Santa 2024 competitions. In this talk, I will first briefly introduce our backgrounds. Then I will provide a summary for all our solutions. Following that, we'll explain the two key differentiators, our search algorithm and the pruning method using a lightweight neural network. Finally, I will touch on some experimental approaches that were not included in our final solution, but maybe still of interest. Okay, so the background. Our team consists of 3 Kaggle competition grandmasters, each with a different professional backgrounds. Nagis is a data scientist at a tech company, and C number is a PhD student in physics, and I'm a quant at an investment bank. But we share an expertise in numerical analysis, and notably, all of us have participated in Japan's well-known competitive programming contests. So this experience helped us rapidly implement the algorithmic and heuristic optimization techniques. It's an advantage in this competition, I think. We also have a deep passion for Santa competitions, as you see in the screen, and would like to take this opportunity to express our gratitude to the admins who organizing it each year. Actually, we've got to know each other on the Santa leaderboards, I think. Next is a solution overview. To briefly summarize the competition task, it was a combinatorial optimization problem where the objective function was computed by a LLM, and the perplexity calculation was computationally very expensive and near black box, making it difficult to apply existing heuristic solutions or some program-specific techniques. However, we assume that, of course, similar texts will likely have similar scores, and that means neighborhood search is a still viable approach. Now, also, it was crucial to optimize the search process to minimize the number of calls to the JMA model for scoring. Well, in essence, our approach can be described as an iterative local search method enhanced with neural network-based pruning. So we improve the candidate solutions through local search and applied perturbations when reaching the local optima, and also use the lightweight neural network to estimate the scores and prune unpromising candidate. While this sounds very simple in principle, I will now break down the details on each steps. Okay. Search algorithms. Our search process begins by generating the neighboring solutions based on the current best solution. We employed 2 types of operations. The first is just an insertion, moving a short word sequence to the different random positions. And the other is finding already sorted subsequences within the solution and insert short random sequences to it and resort the segment. Through the observations, we noticed that the sorted segment frequently appeared in good solutions, leading us to exploit this property. And this property is also mentioned in the public discussion, I think. And yeah, we enumerated the neighboring solution using these 2 operations and then applied the depth first search for the hill climbing or greedy search. And each neighbors was evaluated by JMA, and if the candidate had a lower perplexity than the current best solution, we accepted it and continued the search. We also introduced threshold-based DFS strategy that allowing us to accept non-improving solutions up to a certain limit to escape shallow local optima. This method, this DFS enable deeper and more effective local searches. Despite that, the operation itself are not too complex, I think. It is effectively enhanced to include other many kind of neighborhood operations. The DFS acceptance threshold was like this plot. Higher tolerance at the shallow depths and gradually tightening at the deeper levels. This approach maybe resembles simulated unlaying in that it allows escaping the local optima on a smaller scale, but this is deterministic search. And kick strategy. Despite our enhanced DFS, local optima is still a challenge. To escape these, we used a kick mechanism which applied strong permutation, such as multiple random swaps or just segment destructions. Since excessive permutation sometimes made it impossible to return even to the known solutions, we implemented a restart mechanism to revert to the best solution when necessary. Here is just an example of score transition during the search. The x-axis represents the total such steps count, and the y-axis shows the perplexity score for the problem ID 5, I guess. The local search steadily improves the score, then undergoes large jumps due to the kicks. But it ultimately reaches a better solution than before. To improve the efficiency, we also incorporated several additional techniques, such as early terminations of local search and batch computation for JAMA evaluations, and also casting of computed scores. It is simply used in the following search, but also used in the training of the pruning model that I will describe in the next sections. At this stage, we have achieved a competitive result with only a few improvements left to the solutions, if I remember correctly. Next is neural network-based pruning. The key challenge was the high computational cost of scoring via JAMA. And although completely replacing it with a distilled model seemed too difficult, we thought that detecting obviously poor candidate for only pruning was somewhat feasible. To achieve this, we use a lightweight one-dimensional CNN, which was trained online during the search. The model did not need to predict the absolute scores accurately. Instead, it needed to maintain the correct rankings or correlations among the candidate solutions. Our model architecture was one-dimensional ResNet with switch and excitation blocks, where input sequences were embedded, and the model was trained to minimize L1 loss against the perplexity, actual perplexity. The L1 loss was chosen for its robustness to outliers, making it well suited for maintaining the score correlation. With this neural network-based pruning, our final search procedure was as follows. The new additions are highlighted in blue. Now, since the neural network was trained online, we applied an Epsilon greedy-like strategy. it keeps small number of random candidates to prevent biases in the training data. And this overall pruning method could significantly accelerate the search and allowing us to find the winning solution within 2 weeks or 3 weeks or so of the competition start. And finally, I will briefly mention some approaches we experimented, but did not include it in our final solutions. After achieving the winning score, we of course, continued exploring potential improvements. Of course, we didn't know it is a global optimum or best achievable score during the competition. But eventually, none of these led to better results, unfortunately, at least by the competition's end. One major approach we tested was the beam search. So it was maybe closer to genetic algorithm with local search. I mean, we maintained the multiple solution candidate at the same time, optimizing them while preserving diversity using some criteria, such as edge entropy or size of longest common subsequences in each other. This method tries to search and explore solution spaces. So instead of it keeps expanding the beam widths and explore the more and more potential solutions may be more appropriate, but it seems to slow down the search again. And we also experimented with best first search instead of DFS, but it appears it slowed down the search. And additionally, while we initially worried about the biases in the neural network training data, but it seemed to be a non-issue. And other standard optimization methods such as simulated annealing and genetic algorithms and Linfos, which was introduced in the public discussion, were also tested. But we thought it did not outperform ILS in terms of search speed and adaptivity in the search method improvements. But it is so interesting to see other teams succeeded to obtain the best scores using these algorithms. Conclusion. To summarize, our iterated local search method enhanced by lightweight neural network was highly effective under the computational constraints. By leveraging the observation of sorted segment in good solution, and also DFS-based local search and key populations, these cover the wide search space enough. And furthermore, the neural lightweight estimator-based pruning with caching and batch evaluations. These all drastically reduce the cost of GML scoring and leading us to our final solution efficiently. This concludes my presentation, and thank you for attention. I will be happy to answer any questions, if any.